let's have a look at the kinetics of zero order reaction. Now you know that the order of a reaction is the sum of the powers of the concentration terms of the reactants in the experimentally determined rate equation for the reaction. Now let's see two examples, one or two examples of zero order reactions. Now one example is the formation of HCl from hydrogen and chlorine in the presence of light. Okay, and its rate equation is written as K into concentration of hydrogen to the power of 0 into concentration of chlorine to the power of 0. Another example is decomposition of ammonia to nitrogen and hydrogen. Okay, and here also the rate is written as K into concentration of ammonia to the power of 0. Alright, so that means the rate is independent on the reactant concentration. The rate of the reaction is independent on the reactant concentration. Now let us take up a general example, general reaction A giving product P, reactant A giving product P. Now the rate of this, if we are assuming this to be a zero order reaction, then the rate equation will be rate equal to K into concentration of A to the power of 0, right? Now the same rate can also be written in terms of decrease in concentration of A as rate equal to minus dA by dt. This can also be written as rate equal to K into concentration of A to the power of 0. Alright, and now we can since A to the power of 0 will be 1, we can rewrite this equation as rate equal to minus dA by dt, which is equal to the rate constant K. Okay, now we have to derive the integrated rate equation for zero order reaction, and for that we need to take up a few assumptions. Now let us first assume that the initial concentration of the reactant be A moles per liter. Okay, as usual, the usual assumptions we have been doing for first order reaction, second order reaction, etc. And let X moles, it must be moles per liter. X moles per liter of A has reacted after time t and formed product P, then the concentration of A at time t will be A minus X moles per liter. Okay, so X, this is moles per liter, I repeat once more, X moles per liter of A has been reacted. So the remaining A at time t will be A minus X moles per liter. And the concentration of product P will be X moles per liter. Keeping all these assumptions in our mind, we can write the rate equation as rate equal to minus d into A minus X by dt. That is equal to K into A minus X to the power of 0. Right, where A minus X is the concentration of the reactant at time t. Now we can carry out the in terms of, we can write this equation in terms of the formation of product like dx by dt equal to K into A minus X to the power of 0. And then we can write dx by dt equal to K, since A minus X to the power of 0 will be 1. Okay, then dx is equal to K dt. We can rearrange this equation 3, you get equation 4. Integrate equation 4. When you integrate equation 4, you get the solution as x equal to kt. Okay, now rearrange this, you get k is equal to x by t. Right? You rearrange equation 6, you get k equal to x by t. Now that is the integrated rate equation for zero order reaction. Okay, k equal to x by t. And that shows that the rate constant is directly proportional to the initial concentration, or sorry, not initial, it is directly proportional to the concentration of the reactant. Right? Now, this integrated rate expression can also be written as K equal to C0 minus Ct by T, where C0 is the initial concentration of the reactant, Ct is the concentration of the reactant at time t. Okay, and so you will get x is x is nothing but C0 minus Ct. Now from this you can arrive at the unit of the rate constant, which is moles per liter per second. Okay, moles per liter is the unit of the concentration, and the second is the unit of time. So moles per liter per second is the unit for the rate constant of zero order reaction. This you have to remember. Okay, all the units for the rate constant of different various reactions, first order, second order, zero order reactions, etc. you must remember. Alright, now coming to the graphical representation of the zero order reaction, we have the x-axis on which we will be plotting the time, and we have the y-axis, and on x-axis we will plot the time t, and on y-axis we will plot a minus x or ct. Okay, so when you plot a minus x versus time, you get a graph, a plot with a negative slope, a straight line with a negative slope and an intercept. The slope will give you the value of minus k, and from there you can get the value of k, the rate constant, and the intercept is equal to the initial concentration A of the reactant. Okay, so this will be the plot of A minus x or Ct against time for a zero order reaction. Alright, now one more aspect we have to check, and that is the time taken for fractional order. The time taken for the reaction to complete into certain fractions. Okay, so fractional change. So let us come up with the half-life period. First, T half. You know, T half is nothing but the time taken for the completion of half of the reaction, or time taken for the conversion of reactant to half of its initial concentration. And hence, now we have the integrated rate equation k equal to x by t, and when t is equal to T half, x will be equal to a by 2, where a is the initial concentration and x is the concentration of the product. Okay, x will be equal to a by 2. You can substitute this in equation, in the integrated rate equation. You get k equal to a by 2 by T half. Right, the rate constant k is equal to a by 2 by T half. Now you can simplify that, and you will get k equal to a by 2 into T half. Alright, or you can rearrange this and you get the expression for T half. T half is equal to a by 2k. T half is equal to a by 2k. So for the zero order reaction, the half-life period of the reaction is directly proportional to the initial concentration of the reactant, and it is equal to a by 2 by k. A by 2k. Okay. Now this this equation can be extended to various other fractional changes also, like t 3 by 4, t 1 by 4, etc. Okay. Now, when the time taken for completion of a zero order reaction is given by the equation a by k, where a is the initial concentration of the reactant and k is the rate constant. So once we get the value of k from the graph, you can always substitute it and predict the time at which the reaction will be completed. Alright, so that is regarding the fractional change. Now, let us summarize this and put it as the characteristics of zero order reactions. The first feature is that for a zero order reaction, the rate is independent of the concentration of the reactants. And then all zero order reactions must obey the zero order integrated rate equation k equal to x by t. And here k is the rate constant, x is the decrease in reactant concentration or the concentration of the product, and time is t. T is the time. The unit of zero order rate constant k is moles per liter per second, and for a zero order reaction T half is equal to a by 2k. Alright, and we must also remember that the graph is graph of a minus x or ct versus time will be giving a plot with negative slope. and the slope will be minus k. Now this equation t half equal to a by 2k shows that the t half is proportional to the or directly proportional to the initial concentration of the reactant. Alright, so these are the informations regarding the zero order reactions. You must be thorough with the derivation, and also the you must familiarize yourself with the various equations and the graph also, and try to do problems related to the finding of t half, t3 by 4, and time of completion, etc. Okay. Thank you. If you have any clarifications to be done, please feel free to ask. Thank you.